Now let's look at limits of a function at positive or negative infinity. Limits at infinity mean that we're looking at what's happening to the graph as x goes to positive infinity or as x goes to negative infinity. So we say the following: a function f has a limit L as x increases without bounds, which means x is going to positive infinity, if the limit as x approaches infinity of f of x is equal to L, or you can say if the function is getting closer and closer to some number L as x approaches infinity. Similarly, the limit as x approaches negative infinity of a function is equal to m if you can show that the function is getting closer and closer to that number m as x approaches negative infinity. So let's use the graph to figure this out for the next few examples. Let's find the limit as x approaches infinity of f of x. Well, x approaches infinity means we're going off towards the right on the x-axis. We'll take a look at this blue graph. It seems like it's getting closer and closer and closer to the x-axis. Well, we know the x-axis is at the location of y equals 0. So the limit as x approaches infinity of f of x is equal to 0. Well, what about the limit as x approaches a negative infinity of f of x? Well, again, that means I'm going off towards the left side of my x-axis. So if we look here, well, this graph seems to be closer and closer and closer to the x-axis, which is y equals 0. So the limit as x approaches negative infinity of this function is also 0. Let's look at example number 5. What's the limit as x approaches infinity of this function? So as we're going off towards positive infinity here, where's my graph going? Well, it's going up and up and up and up and up, which means that this guy is going to positive infinity. So the limit as x approaches infinity of f of x, in this case, is positive infinity. Recall, this means our limit doesn't exist. It just describes the behavior of the graph. What about the limit as x approaches negative infinity of f of x? Again, that means you're looking off to the left. Well, where's this function going off to the left? It's going up and up and up. Also positive infinity. So the limit as x approaches negative infinity of f of x in this case is equal to positive infinity as well. Well, that's wonderful again if we have the graph, but what happens if we don't have a graph? How do we figure this stuff out? Theorem for limits of power functions at infinity. We're going to say that n is greater than 0, which just means it's a positive real number, and k is going to be any real number, it's just a constant, where k doesn't equal 0. Then the following is true. The limit as x approaches infinity of a constant over x to the n is going to equal 0. Same thing here. The limit as x approaches negative infinity of a constant over x to the n is equal to 0. So if you have a number over x to any power, then you're going to be approaching 0 as you go to negative or positive infinity. If x to the n is not in the denominator, so if it's just k times x to the n, then as you're approaching positive or negative infinity, the answer is going to be positive or negative infinity. It's going to just depend on the coefficient and the power. It's going to depend on the coefficient and the power. So two things are happening here. One of these is a rational function, and the other one of these is what's known as a polynomial function. So when you have rational functions and you're trying to find the limit at positive and negative infinity, and only when you're trying to find the limits at positive and negative infinity, to figure out what's happening, you want to divide each term in the numerator and the denominator by the highest power of x in the denominator and use the theorem above here to figure out what's going on. If you don't have a rational function, and you have a polynomial function, and again you're looking at limits at positive or negative infinity, what we do is we determine what the leading term is. That's going to be the term with the highest degree of our polynomial, and then use this theorem above in order to evaluate the limit. So let's look at some examples where we are doing this. Find the indicated limit. We have the limit as x approaches infinity of 1 over x squared. Well, this guy is our rational function, right? How do I know it's a rational function? Because it's a fraction. So what we need to do in this case, right, is divide each term in the numerator and the denominator by the highest power of x and use the theorem above. We don't really have to do it for this one because it's already in the right format to use this theorem. This theorem says, hey, if you're going either to positive or to negative infinity, and it's just a number over x to a power, that's equal to 0. So if we look here, the limit as x approaches infinity of 1 over x squared, this is in the correct format to use my theorem. This is just going to equal 0. Why? Because anytime you have a number over x to a power, it's equal to 0. I'm going to skip to number 8 and then come back to number 7. Number 8 is also a rational function, but it's not in the same format as the one above, right? The one above is just a number over x to a power. So for a rational function here, where it's not just one number over, what we want to do is we want to divide each term in the numerator and denominator by the highest power of x in the denominator. So the highest power of x in the denominator in this case is x to the 6th power. So we're going to rewrite this as the limit as x goes to infinity of x to the 5th over x to the 6th minus x cubed over x to the 6th plus x over x to the 6th minus 1 over x to the 6th. And all of that gets divided by x to the 6th over x to the 6th plus 2x squared over x to the 6th plus 1 over x to the 6th. And let's simplify this now. Now, if I have x to the 5th over x to the 6th, that simplifies or reduces to 1 over x. This becomes x cubed over x to the 6th, if I reduce it, 1 over x cubed. X over x to the 6th is 1 over x to the 5th. Minus 1 over x to the 6th, I can't reduce that. Over x to the 6th over x to the 6th is 1, plus 2x squared over x to the 6th is 2 over x to the 4th, plus 1 over x to the 6th, that can't be reduced. And now we're going to use the theorem above. So what does the theorem above say? Anytime you take the limit as x approaches infinity and you have a number over x to a power, each one of those is going to be equal to 0. So in this case, this is going to be equal to 0 minus 0 plus 0 minus 0 over, well, what's the limit as x approaches infinity of a constant? Recall from section 2.1, the limit as x approaches infinity of a constant is the constant. So in this case, we have 1. And then here, the limit as x approaches infinity of 2 over x to the 4th is plus 0 plus 0. So if we work all this out, we have 0 in the numerator, 1 in the denominator. 0 divided by 1 is 0. So the limit as x approaches infinity of x to the 5th minus x cubed plus x minus 1 over x squared plus 2x squared plus 1 is equal to 0. So, shortcut way of doing this, because that is a lot of work, right? Shortcut way of doing this. What we want to do is the following. We go back and we look at what's the given. This is my given rational function. I really only care about the highest term in the numerator and the highest term in the denominator. So I have really just x to the 5th over x to the 6th, right? Because the largest term in the numerator is x to the 5th, and the largest term in the denominator is x to the 6th. So that's going to reduce to this 1 over x. This will reduce to the 1 over x. Well, what's the limit as x approaches infinity of 1 over x? Well, that's going to be 0. And that's going to determine the whole entire thing for us. And that's going to give us our answer of 0. Let's do number 9, and I promise we'll come back to number 7. So we're going to do number 9 kind of the same way that we just did the shortcut here. Again, you realize, hey, this is a rational function. So what's the largest power in my numerator? X cubed. What's the largest power in my denominator? X cubed. So really, I'm just looking at what's the limit as x approaches negative infinity of x cubed over x cubed. Well, if I reduce that, that's really just the limit as x approaches negative infinity of, well, x cubed over x cubed is 1. Well, what's the limit of a constant? The limit as x approaches negative infinity of 1 is equal to 1. So the limit as x approaches negative infinity of x cubed plus 2x squared minus 5 over x cubed plus 7x squared plus x is equal to 1. All right, let's go back to number 7, and then we'll keep on going. Number 7 is different. This guy is a polynomial. This is not a rational function anymore. How do I know that? There's no fractional bar. So this is a polynomial. So what do we do with polynomials? Well, what we need to do is we look for the leading term. That's the term with the highest degree, and then use the theorem above. All right, what's the term with the highest degree? Is 3x cubed. So really, we just care about what's the limit as x approaches negative infinity of 3x cubed. When you take negative infinity and you cube it, so you take a negative number and you cube it. So negative times a negative times a negative, it stays as a negative infinity. When you take the number 3 and you multiply it by negative infinity, it's going to stay as negative infinity. So the limit as x approaches negative infinity of this 3x cubed plus x squared plus 1 is going to equal negative infinity. Because that highest term is really what's going to determine what's going on in terms of the behavior of the graph. All right, let's look at number 10. So number 10 is also a rational function. So what we're going to do is exactly what we did before. What's the highest power in the numerator? X to the fourth. What's the highest power in the denominator? X squared. So this is really just the same as looking at the limit as x approaches negative infinity of x to the fourth over x squared. Well, if I clean that up, that's the same as looking at the limit as x approaches negative infinity of x squared. Okay, well, I just got rid of my fraction, and this now became a polynomial. Well, I just have to think about, okay, what happens when I take negative infinity and I square it? Well, that's negative times a negative. Two negatives equal a positive, therefore this is equal to positive infinity. So the limit as x approaches negative infinity of x to the fourth plus x squared minus 2 all over x squared plus x minus 1 is equal to positive infinity.